Today we do variation of parameters.
Forgot about that.
Variation of parameters. Okay, let me solve the typical question for a variation of parameters. Y double times y equals to tangent of x. Now you have to start with the complementary solution, right? Start with complementary, which is the solution of the homogeneous equation on the right side. And because this has the characteristic equation r squared plus 1 equal to 0, and the solution is, if you move it to the other side, it's -1. Square root of -1 is I, so you get plus or minus I. In that case, if you have 0 plus minus 1I, the solution should look like e to the 0x times c1 cosine 1x plus c2 sine 1x. I'm just trying to remind you that in general, if you have the solution of the characteristic equation as a complex number, the solutions come out to be some exponential function times cosine or sine, depending on this variable. If it's a plus minus bi, it should be e to the ax times cosine bx. And the second one is e to the ax times sine of bx. But because they both have e to the ax as common, usually you pull that out. You write down your complementary solution that way. For our case, it's really simple because e to the 0th power is 1. So it's simply c1 cosine x plus c2 sine x. That's the complementary solution. And then after you get the complementary solution, the next step is to use some method to find out the particular solution, right? But the problem is the particular solution has a derivative which doesn't get simplified over the time, right? So if you differentiate tangent x, what happens? Secant squared. If you differentiate secant squared, you get secant cubed tangent x. No. 2 times secant x, 2 times secant squared x times tangent x. And if you differentiate it even again, you get 2 times secant to the 4th. I can't even say. It just becomes more and more complicated. So that means when you try to use the method of undetermined coefficients, you fail. It doesn't work. Because for the method of undetermined coefficients to work, you're supposed to have y of p as this thing along with all the possible derivatives, right? But if the derivative doesn't repeat itself, then you end up writing infinitely many terms and it just fails. It doesn't work that way, okay? All right, so once you're convinced that the usual method, the easier method, which we call the method of undetermined coefficient, doesn't work for our case, then you have to resort to another case, which is called the variation of parameters. And by parameters, I mean these, right? These are called parameters. And the variation of parameters method will sometimes give you an answer, but if it doesn't give you an answer, it will at least always give you an answer in some integral form. And that's still good in terms of numerical standpoint, because if you're trying to find a solution in a numerical way, usually approximating integrals is easier and more accurate than trying to approximate your derivatives. So if you can find your answer at least as integral of some form, it's something better than having just the differential function. All right, so let me try to explain what variation of parameters is. Okay, so notice that these are constants, right? C1 is a constant, C2 is a constant. Variation of parameters says that what you want to do is to come up with a solution that looks like functions instead of constants. That's what variation of parameters is. So your goal is the following. You plug this back in here to find one particular solution. That's what you do. Right? And once you find that one particular solution, again, you add to yc. Yc plus yp gives you the general solution. That's the idea. Now, however, even before trying this out, you see that something is not right because you have two unknowns, right? You have two functions that you don't know. And how many equations is this? Just a single equation, right? So even before trying, you need that, you realize that you need another condition than just having this, because this is not enough to give you a good condition, right? So here's the extra condition that people do. First, when you differentiate this, let's try to differentiate, then you have u1 prime of x cosine of x plus u1 of x times negative sine of x. That's just the product rule applied to the first part. Right? Then if I differentiate this using the product rule, it's u2 prime of x sine x plus u2 of x times cosine of x. And the condition, extra condition that people put is this condition, that this should equal to 0. So if we say u1 prime of x cosine of x plus u2 prime of x sine of x equal to 0, then that's going to give us one condition, and that has the additional effect of simplifying your derivative, so it's easier to compute. So you actually, in order to plug this thing into this equation, you have to differentiate one more time, right? Like, think about trying to differentiate this itself without this condition. That's going to be a very big mess, right? So this kind of helps, right? And another good thing is that since this gives you an additional equation, if I plug this thing into here, I get another equation. So we have two equations for two unknowns, and that's good. Okay. So those are the reasons why you want such a thing. And I guess the third reason is that at the end of the day, it works. Yeah, that's the good thing. Okay. Somehow, if you put this extra condition in, then everything works out, and it's good. Okay. So let's try. Since that's 0, we have just y prime p being this one, and y double prime of p is therefore. We now have to apply the product rule for both of them. So if I differentiate this, it's negative u1 prime of x sine x. And then when I differentiate this, that's cosine, so it's negative u1 of x cosine of x. Okay. And then when I differentiate this, it's plus u2 prime of x cosine x And then when you differentiate cosine, it's negative sine, so it's negative u2 x sine of x. That's your y double prime. Now let's plug in this thing in here, that thing in here, and let's see what this equation becomes. Let's see what this equation becomes. This equation now becomes okay, first y double prime is this thing, so let's just copy this down. It's negative u1 prime of x sine of x minus u1x cosine x plus u2 prime of x cosine x minus u2 sine of x plus, that's y double prime. And then I need a y, so let's copy that down. u1x cosine x plus u2x sine x. And on the right side, it's equal to tangent of x. Okay, let's go back and check if anything gets simplified. Do you see anything getting canceled?
Negative u1 cosine of x and the u1 cosine of x.
And then
The u2 sine x.
those cancel. Okay? So you end up with the simplified equation, which is that negative u1 prime of x sine of x plus u2 prime of x cosine of x equals to tangent of x. That's what we get, u1 prime x. And this is the second equation. Putting these two together, now we can figure out what u1 prime and u2 prime are. Okay? Now let's stop here for a moment and think about why this ended up giving us such an easy answer. Well, see, the reason this plugged into this gave us such an easy outcome was, or another way to say it is that the reason that you had so many cancellations was because that cosine and sine happened to be the complementary solution to this equation. So cosine and sines are something that when you plug into the left side, it gives you 0. Okay? And because even when you apply the product rule, one part of it is like what you would get if u1 was a constant, right? If you were differentiating this, and if this u1 was a constant, then this is all you would get, right? So always when you apply the product rule, you get two terms where one term would be as if the other one is constant, right? So even after treating these C1s and C2 into functions, if we promote it to functions and you plug in, with some additional, because we had these cosine and sines that were complementary, at the end of the day, we were going to expect some cancellations. So that's the theory behind, or that's the idea behind this variation of parameters. Use the complementary solution, somehow tweak it a little bit so that you can end up with the particular solution. That's the idea. Yes?
How do you get u1 prime x cosine x plus u2 prime x sine x equal to 0?
This one, this was an additional condition. That's,
Okay, so that'd be given?
Oh yeah. This is what we will always assume. Okay, when you're applying the variation of parameters, you will always assume that we have such a thing. Thank you for asking me that question. Yeah, that's a good question. All right, so we always make this assumption because we are free to make one extra assumption. We only have one condition for two unknowns. Therefore, even if we assume this extra condition, we can still come up with two functions that will satisfy both. Okay? All right, so now let's actually solve this. How do we solve this? Well, let's solve for one of the variables and plug into the next one. That's how you solve it, right? So let's try to solve this one by u1 prime of x. So u1 prime of x cosine of x is negative u2 prime of x sine x. And then we divide by cosine x, so that the cosines cancel, leaving you with u1 prime of x equals to negative sine x over cosine x, which by the way is tangent x, right? So it's not too bad. All right, now we can plug this into the top one. We made use of this one. Now we have to use this one. And if I plug that in here, I get negative of negative, that's positive. And you get sine of x, cosine of x, u2 prime of x, plus u2 prime of x. Oh, sorry, there's a sine x afterwards, sorry. So this much, after canceling the minus, this much is negative u1 prime of x, and then I still have sine of x attached. And then there's the plus u2 prime of x, cosine of x. And let's write down the tangent of x as sine x over cosine x. Because now I want to multiply cosine all the way to get rid of the cosines. So all the cosines can be deleted if I multiply cosine x, which gives you sine x, sine squared, sine times sine is sine squared of x times u2 prime of x, plus cosine squared of x, u2 prime of x, equals to sine x. That's what I get after multiplying cosine x everywhere. So both of these cosine x in the denominator went away. And then because I multiply cosine to cosine, I get cosine squared. And that's nice, because what's sine squared plus cosine squared?
1.
1. So you have, after factoring out the u2 prime of x, since this is just equal to 1, you end up with u2 prime of x equal to sine of x. And then going back, plugging this into here gives you that u1 prime of x is negative sine squared of x over cosine of x. All right, so we're almost there. See, what are we aiming for again? We're looking for yp, right? In order to find yp, what do we need to know?
U1 and U2.
u1 and u2. Do we have u1 and u2?
Just take the algorithm.
We don't yet, but it's very close. From here, we know what's u2, right? What's u2?
Negative cosine.
Negative cosine. Integrating sine, it gives you negative cosine. This one's slightly harder to integrate. I mean, you can rewrite this as sine squared is 1 minus cosine squared of x over cosine of x, which is negative 1 over cosine of x, and then minus, negative is plus cosine of x. Okay. So if you integrate, therefore, u2 prime is really 1 over cosine is secant of x, and then cosine is just cosine x, right? So we have to integrate this. So what is u1 of x? Does anyone know the integral of secant x?
Secant x, right?
No, that's the derivative. Integral of secant x. Hmm?
What is it?
ln of
1 over x, right? Or
secant x plus tangent x. Okay? That's the integral of secant x. And then cosine integrates to sine x. That's U1x. All right, so we've come a long way, but let's try to organize it. Oh, by the way, since I'm not 100% sure that the integral is right,
There's so many arrows.
It's like a treasure map.
let me do a quick check, okay? I'm pretty sure that's the right one, but let's see. What do you get if you integrate, differentiate secant x plus tangent x? This is ln of f is f prime over f, right? So we have to differentiate secant of x plus tangent x, and divided by secant x plus tangent x. Secant differentiate to secant x tangent x, and this is secant squared of x over secant x plus tangent x. And if you factor the secant x on the top, you end up with tangent x plus secant x divided by secant x plus tangent x. And what a surprise, these are the same thing, right? So if you cancel them, you end up with secant x. So we verify that really the derivative of this is secant x, therefore integral of this is that, okay? All right, so that we know. So now we can say yp is ln, actually with the minus sign, minus ln secant x plus tangent x plus sine x times cosine x plus u2 is negative cosine x times sine x. Okay. We found our u2 and u1 from there. I plugged them in. And even this can be simplified, because if I simplify, I end up with negative ln secant of x plus tangent of x cosine of x. And sine times cosine minus cosine sine x, they cancel, right? These two cancel. And that's it. That's our particular. Kind of amazing that this would be the solution of this. Who would have thought? But that's the solution. And therefore, what is the general solution? What's the final answer? Answer is y is yc plus yp, which is c1 cosine x plus c2 sine x minus ln secant of x plus tangent of x times cosine of x. That's it. That's how you solve it. Yes?
How do you go from negative ln cosine x plus negative cosine x sine x to just ln secant of x plus tan x?
Oh, I was just pointing out that
I know, I kind of lost track.
these are exactly same and with opposite signs. So if you add them, it's 0, right?
Okay.
Yeah, right? If I multiply them, sine times cosine minus cosine times sine, that's 0, right? Because this is same as, I can switch these two places. Multiplication is commutative. So negative cosine times sine is negative sine times cosine. And they're the exact same thing, so they cancel. Right?
But if you get 0, then where do you get the cosine from?
No, this cosine is by, you distribute first.
Oh, okay.
Cosine gets multiplied to each one of them.
Oh, okay.
And then
Sorry.
this will cancel
Yeah.
with that. Yeah,
There you
that's
go.
how it works. Do you have any other questions? All right, let's